Hello everyone, welcome back to Calculus 3. Today in this video clip, I'm going to cover the very last two sections of our course, section 16.8 and 16.9. We'll be talking about the Stokes theorem and the divergence theorem. So first of all, we start with the Stokes theorem. Stokes theorem is a more general case of the green theorems that you guys learned before. So let's recall the green theorems. Green theorems say what? If you want to calculate the line integral on a low closed curve, f times dr, I'll write in vector form, okay? Where f is pq, just two-dimensional, and r is xy, so like dr is dx dy. So this is, which is integral of pq dot d of xy, dx dy, which is p dx plus q dy integral. And the green theorem say what? This green theorem, okay? This integral will be equal to the double integral of dq over dx minus dp over dy times dA. Let me double check. Yeah, where the closed integral C right here is staying on the xy plane. Okay, this is C. Okay, and this is the region A that we're talking about. Okay, so the line integral, closed curve integral green theorem say what? The curve line integral with the closed curve right here will be equal to the double integral of the area, the region, and closed by that curve. Okay. Now, Stokes theorem, I'm going to say that idea. The region that we're talking about, the curve right here, the region may not be flat on the xy plane anymore. In other words, if you have, this is your closed curve C right here, and this is the region that we're talking about. This is the region. Okay? You're not on the xy plane, it may not be flat anymore. And the formula still works. From integrating along that closed curve C right here, we can integrate on the area. The area we don't call A anymore. But this region we call what? ds. And we just learned it last time. Okay, so let me state the Stokes theorem. And by the way, since this is the surface in terms of vector, you have something we used to talk about last time, the normal vector. And you have something called the unit normal vector. Okay. If you have S, can be represented as vector R, UV, parametric curve, then the normal vector is what? RU plus RV, and make it unit by divided by the magnitude RU plus RV. Okay. So, let me use this, keep the same notation right here. The Stokes theorem say what? You have a surface, now it's not flat anymore, may not be flat anymore, okay? And you have a closed curve and closed surface S right there, okay? And the line integral of the vector field F times dr, R is a line right here. See right here. Okay? And according to the Stokes theorem, this is a green theorem. Stokes theorem say what? This will be equal to the double integral of curve F times ds. This is the S that we're talking about right here. Okay? This is S vector. Okay? And as we learned before from a previous section, ds is, this is curve F, and ds is what? The normal vector times ds. Now I'm writing that without a vector. Okay? ds right here is normal. It's the definition of the surface integral that we learned last time. Okay? Vector times ds is vector. Vector is not f, it's a curve field, curve of f, I mean. Okay? And then Well, n here is the unit normal vector. Okay, that's all about the Stokes theorem. So I think I should give you an example. Okay, example. Use the example in the book. Calculate the line integral f dr, where f is, just copy it here. Example, f is what? Negative y squared, comma x, comma z, okay? Oh, z squared, okay? Just copy it, right? And then the line, the curve C is what? The intersections of the plane x plus z, y plus z equal to 2 and the cylinder. So this is what? Y plus z equal to 2. This is the plane, okay? And then intersection with x squared plus y squared equal to 1. And this is the cylinder. Now let me try to draw the picture for you. You see it. All right. I claim with this problem you can actually do the line integral. It would work as well. You parameterize it and you can do a line integral. But we're going to use the Stokes theorem. I think it's going to be easier. That's why I put it here. So this is the cylinder. Okay. You see the cylinder, and then the x plus z, y plus z equal to 2 is the plane intersect the cylinder. See? So the intersection is going to be that curve, that slash right here. You imagine that we have a tube going up. Okay? This is a tube going up, x squared plus y squared equal to 1. This is circle of radius 1. Okay? Going up, this is the y-axis right here. This is the x-axis right here. This is the z-axis. Okay? And the plane y plus z equal to 2. It's going to be this way. And it's going to cut the cylinder and cut this ellipse. It looks like this. And this is the curve C that we're talking about. And by the way, the book says it says positive orientation means what? It go counterclockwise. I mean, imagine that you walk along the curve, then the region, the area is on the left-hand side of you, so it's counterclockwise. Okay, so positive orientation. Of course, if you walk backward this way, the region is on your right-hand side, and what? It's a negative orientation. Okay. And the integral pretty much the same. It's just opposite by the sign. And same thing here. If you point the normal vector upward, then you have a positive, right? You point the normal vector could be this way, a negative. Then the integral is the same, exactly the same. It's just opposite sign. And in terms of flux and physics, right? If it's coming out, then positive, right? And if you calculate it, you have a negative, means what? The flux is not going to go this way; it's go the other way. So vector pointing the other way. That's it. And it's the same in math. All right, so how do we apply the Stokes theorem to calculate the integral f dr on the curve C? The curve C is this. Okay, so let's do it. So I have the, oh, I erased it. So let's rewrite it here. F was what? Negative y squared, x, and z squared, okay? And I have the curve right here. I erased it, but I draw it right here. This plane right here is y plus z equal to 2. And this cylinder right here is x squared plus y squared equal to 1. Intersection is going to be the curve C that way. Okay, so first of all, we're going to calculate curve F, right? This is F right here. Recall how to calculate curve F. What was that? Curve F. I, J, K, what? D over dx, D over dy, D over dz, right? And this is PQR, so negative y squared, x, and z squared. Okay, well, let's do it. So for the I term, dz squared over dy is 0 minus this is going to be, so the first term is going to be 0 because the derivative of z squared over y is 0, and then the derivative of x over z is 0, and then this is 0. For the second term, for the j term, dz squared over dx is 0, minus become plus, dy squared over dz is 0, with negative 0 still 0, and then for the k term, dx over x is 1, minus with minus become plus, dy squared over 1 is plus 2y. It's easy, huh? So curve f is 0, 0, 1 plus 2y. And as you see right here, the graph is actually a function. Okay? The function, this is a function because it passed the vertical line test, so I can use the equation for the function. Let me see. This is the f, right? So curve f right here, double integral, curve f is 0, 0, 1 plus 2y, okay? And now ds, we learned last time, is a function, so what do we have for function? Let me look it back. Let's see. Oh yeah, ds right here was dg over dx, negative dg over dy, and then 1, and then dA. This is ds, right? It was a function. Look back to your note from last time. So this is really cross what? Negative dg over dx, negative dg over dy, comma 1, and then dA. So how you dot the two vectors, 0 times this is 0, 0 times this is 0, and then 1 plus 2y times 1 is 1 plus 2y. So this is double integral of 1 plus 2y, and then dA. dA is supposed to be dx dy, right? But I just erased it, so I have to draw it again. This is the a that you're talking about. It's a circle. It's a unit circle, radius 1. So I better use polar coordinate. It's going to be easier. So if I use polar coordinate, then what? X is r cosine theta, I think, and y is r sine theta. And r is 1 because this is unit circle. X squared plus y squared equal to 1. So r equal to 1. I can have this. And dx, dy, as you guys learned before, this is dA. Now become what? R, dr, d theta. Okay? So this double integral becomes double integral 1 plus 2 times y is r, x is r cosine, so y is r sine theta, and then dA is r, dr, d theta, unit circle, so theta run from 0 to 2 pi, and r run from 0 to 1. Okay, and then you integrate this, you should have the answer. Let me see if I got it right. Yeah. Multiply it all out, okay, and then integrate. I'll leave it for you. Make sure that you guys can do this one. Distribute it, so this is r plus 2r squared sine theta dr d theta, okay, and dr first in here, so r here becomes 1/2 r squared, and this is 2/3 r cubed sine theta. Okay, run from 0. Let me do it. Let me get it done. Not hard, it's not like too easy. So let's do the integral inside. R here, antiderivative is 1/2 r squared, and 2r squared, antiderivative is going to be 2/3 r cubed sine theta, r from 0 to 1. I'm talking about the integral right here inside. And what is it? 1, so it's going to be 1/2 plus 2/3. Oh, that was 1, right? 2/3 of sine theta. And now you integrate this in d theta, run from 0 to 2 pi. This is 1/2. I say 1/2 theta minus 2/3 cosine theta, because antiderivative of sine is cosine, from 0 to 2 pi, and I bet you guys can work it out from here. This is going to be 1/2 2 pi, so like 2 pi, and then 2 pi here goes out, 2 pi is negative 1, with a negative becomes 1, so it's 2, so 4/3, so this is pi minus 4/3, I think. Let's double check on the work. Oh, it's 0, not 2. Cosine of 0 is 1. Yeah. Yeah. 2 pi is also 1. Yeah. So 0. So pi plus 0. 1/2 of 2 pi plus 0. This is pi. That's the final answer. Okay. This is the end of section 16.8. So actually, it's just a special case of the surface integral that you learned. So curve F is really a vector field, right? If you say you have a vector field F, you can calculate curve F, and curve F times ds. However, you're doing here exactly what you did on the previous section. You convert the ds into what? Ru cross Rv times dA. That's how you calculate it. Okay. In special case, and you can do it this way. And the Stokes theorem only applies for the closed curve, if the curve is closed. And it is more advanced than the Green theorem is what? The surface region, the surface area enclosed by the curve, so it may not be flat anymore. It could be smooth. It's got to be smooth, but it could be curvy. Okay, it may not be flat, straight anymore. And it still works. Okay, so the calculation is going to be exactly the same. It's just condition is what the curve got to be close. Okay. Now the last theorem, divergent theorem. 16.9 divergence theorem. Okay. Let me use the same notation as the book. So now we have a theorem that's helped you to convert from double integral to triple integrals. Okay. Stokes theorem basically what? From a line integral, single integral to double integral, right? Now the divergence theorem is going to help you to do to convert from double to triple. So if you have a double integral on the region S of the field F times ds, okay, this is the surface integral. Now I'm writing it into vector form. Okay. And the divergence theorem say what? It's going to be equal to triple integral of divergent. Now you see the word divergent of vector F dv. Okay, and the condition to have this divergence theorem to happen is what? The surface right here is going to be surface of the enclosed solid region. Solid region, yes. So what? You cannot use the divergence theorem if the surface S is like this. Okay, it's not enclosed. But if you have something like this, I just try to draw it as random as possible. And you imagine that we have a box, so the surface S is around. And a simple case of this is a sphere, usually. You guys have a sphere, right? So the surface S is the surface of the sphere. Now what? The region S is enclosed, right? And dV now here makes sense because V here is what? The volume of that sphere. Or in this case right here, V is the volume of that weirdo box that you have, right? So The divergence theorems only work if you have a closed surface. All right, and if it works, if you have a closed surface and double integral vector field F over the surface, it's going to be equal to the triple integral of the divergence of F times the volume. Okay, and recall what's divergent. So you got F, vector F is say P, Q, R, what we learned before. Then divergence of F is dP over dx plus dq over dy plus dr over dz. And believe me, it turns out that what? The math on this one is going to be easy. And dv in here, if you use a rectangle coordinate, it's going to be dx, dy, dz, or you have the cylindrical coordinate, you're going to be, r d theta dz, or if you're going to use the spherical coordinate, going to be rho square sine phi, d rho d sine d phi, d rho d theta d phi. Okay, so this is the main theorem for 16.9. Okay, and the condition is what? That surface S is going to be enclosed in solid region, so we can have the volume. That's it. So let me give you an example. Okay. I think it's in physics because of flux there. Easy. Let me just give you a simple example. We have a sphere, okay? And F is vector field, right? The vector field. Let's say from inside out. Vector field. Yeah, go on now. Okay. And this is really the flux. We talked about this before, and I think it's in section 16.7, 16.6 or something. And this integral will tell you how many vector F that's coming out of the sphere. And it's going to be equal to divergence of F times dV. Okay. How about example? All right, let me use example in the book. The book gives you F is z, y, x. Easy. Okay. Example. F is equal to z, y, x. This is my vector field. And the region that we cover is the sphere. X squared plus y squared plus z squared, well, make it easy, so the unit sphere equal to 1. Okay? This is my S right here. This is my F right there. And sphere is closed, of course, right? Closed. So if it's closed, I can use the divergence theorem, and divergence theorem say what? This double integral on the surface gonna be equal to the triple integral divergence of that vector field on the volume inside that surface. So divergence of F gonna be calculated. Divergence of F will be dz over dx is 0, dy over dy is 1, dz over dx plus dy over dy plus dx over dz. Okay. This is p, q, r. This is p right here. This is q right here. And this is r. Okay. And then p is z, and q is y, and r is x, and this is just 1. Because this is 0, this is 1, this is 0. Okay. So this one is divergence is 1 already. So this is what? Triple integral of 1 dv. Ah, I see it's right away. It's 1 dV, it's just triple integral of dV. And what is it? The volume or whatever region that you cover, right? So this is the volume of the sphere. The volume of sphere is 4 over 3 pi r cubed. R is 1, so 4 over 3 pi. Yeah, piece of cake. Okay. So before we start for the entire course, let me try to summarize the whole idea that we learned in chapter 16. Hopefully that helped you to organize your thought. Okay, this is the end of 16.9 already. Okay. So in chapter 16, what do we learn? We learned that let's say, what's the main thing? Oh well, this is Calc 1 actually. Integral from a to b of f of x dx, well, kind of line integral. We start with this, right? Equal to big F of B minus big F of A, called the fundamental theorem of calculus, okay? Where f prime of x is equal to fx. So usually, this is how you write, right? But you can replace this in here. F of x is f prime of x, okay? We start with this fundamental theorem of calculus. And this is a very special case of line integral. The line is straight line running from A to B on the x-axis, and this is the y-axis, and this is your function f right here. Okay? And now we make it more general. We have a fundamental theorem of the line integral. We have what? The integral on the curve C of gradient f, it's like derivative, okay? Time ds is going to be equal to what? F of, I have the book right here. So it's RB minus F of RA. Line integral. This is called a gradient, right? Of the vector F, conservative thing. Okay? And this is what this is a curve C. Okay. X-axis, y-axis. Z-axis coming out. Okay, this is R A, and this is RB. Vector. Okay. And T is the variable right from A to B. Usually we parameterize in terms of T. T0 right here, T1 right there. Okay. And then we have the Green theorem. And the Green theorem say what? You have a closed regions on the xy plane. Green theorem. Where am I right here? Green theorem. You have a closed curve on the xy plane. Double integral of f times dr, and this is how I usually write it. Okay. The book I write this way is integral of p dx plus q dy. F is p cubic. This is vector field on the two-dimensional space, and then r right here is xy, so dr is dx dy right here, and the Green theorem says what? This is equal to double integral of dq over dx minus dp over dy on the region dA. Okay? And the condition is what? It's going to be a closed curve. Okay, this is the curve C. And after having the Green theorem, we improve it into a more general theorem we call the Stokes theorem. And the Stokes theorem, same idea, now 3D, integral f dr is equal to Stokes, say what? Equal to curve f, I think, double integral of curve f times ds, okay? Or you can write it as double integral of curve f times n times ds, okay? No vector. Okay? And after the Stokes theorem, then we have something called the divergent theorem. Divergent theorem. Okay? So Stokes theorem converts from line integral into double integral. Condition for the Stokes theorem say what? You have a closed curve that encloses a surface. Okay? This is the surface that you enclose. This is the curve C right here. Okay? And this is the surface S that you have. Instead of integrating along the curve, now you can integrate on the regions enclosed by the curve. Okay. And divergent theorem going to convert from surface integrals to double integral. So double integral